Curvilinear coordinate systems 23. Derive the curvilinear divergence considering the possible variation of the scale factors along each surface of the volume. So we're going to do only this part of the problem, and since we have done it already in the lectures, I'm just going to go over this derivation. Now, if we consider the integral definition of divergence, divergence of vector A, according to the integral definition, is limit as S, the area, V, the volume, go to 0, the ratio of the two integrals, closed surface integral d sigma dot A, divided by the volume integral d tau. Now, what is this volume integral d tau? If you remember, our displacement vector dr is h1 dq1 q1 hat plus h2 dq2 q2 hat plus h3 q3 dq3 hat, which is saying that dx is h1 dq1. So we have dx is equal to h1 dq1, dy is equal to h2 dq2, and dz is equal to h3 dq3. So the volume dv or d tau is dx dy dz in Cartesian coordinates. It would be h1 h2 h3 dq1 dq2 dq3. As v goes to 0, this is the volume defined by these dimensions. h1 dq1 dx, h2 dq2 is dy, and h3 dq3 corresponds to dz. Now, looking at the other part of this expression, which is the nominator, the closed surface integral d sigma dot A. Now, for a closed surface, we have to consider the bottom, top, left, right, front, and back contributions. Now, if I look at the figure, for the bottom, I have the dimensions h1 dq1, h2 dq2. Therefore, the area, differential area defined by this is h1 dq1, h2 dq2. But the area vector, d sigma, for the bottom has to point in minus q3 hat direction. Why? It has to be normal to the surface, pointing in the outward direction. So d sigma is minus dq1, dq2, h1, h2, q3 hat. We're taking the dot product of this with the a vector, which means we're looking at a3 component. And a3 component is in q3 hat direction. So this is our a3 vector. The other two components do not have a contribution because we only have a dot product with q3 hat here. The other two unit vectors are orthonormal, so they would give 0 from the dot product. So we have a3 q3 hat dot product with d sigma gives us minus dq1 dq2 h1 h2 a3. If I repeat the same procedure for the top, d sigma dot A, if I look at the top, this time I have again h2 dq2, h1 dq1, but I'm at the top, which means I'm not at q3, but q3 plus dq3. So I have to look at the vector field A's a3 component evaluated at q3 plus dq3 for this discussion. So here I'm going to have the area vector pointing in q3 hat direction as well as a3. So I would have dq1, dq2, h1, h2, a3, but this has to be evaluated at q3 plus dq3. This time d sigma is in q3 hat direction, a3 vector is in q3 hat direction. So for h1, h2, a3 evaluated at q1, q2, q3 plus dq3, I can do a Taylor series expansion. When dq3 is 0, the first term is h1, h2, a3 evaluated at q1, q2, q3. And then the first term is the partial derivative of this with respect to q3 evaluated at q1, q2, q3 multiplied by dq3. So that's the Taylor series expansion first two terms, so up to first order. So that means I have from the top and bottom, so from the top I had this contribution, from the bottom I had this contribution, so those two contributions would cancel out, and I will be left with only this term. Partial derivative h1, h2, a3 with respect to q3, evaluated at q1, q2, q3. So dq3. Now, because I also had dq1 and dq2 here in these terms. So this is just this part evaluated at q3 plus dq3. So this will be in d sigma dot a multiplied by dq1, dq2 also. So that's the contribution from top and bottom surfaces. If I do the same exercise for left, right, front, and back surfaces, instead of this A3, I would have A1. H1, H2 would be H2, H3 with respect to Q1. And then instead of A3, I would have A2. Then I would have H1, H3, the partial derivative with respect to Q2. And this term we already have here. So the total would be this. Now this has to be divided by this term, according to the integral definition. So dq1, dq2, dq3s would cancel out, and I would be left with 1 over h1, h2, h3, the, in parentheses, partial derivative with respect to q1 of h2, h3, a1, plus partial derivative with respect to q2 of h1, h3, a2, plus partial derivative with respect to q3 of h1, h2, a3.